Thank you. So hello, everyone. So once again, my name is Maria, and yes, I'm currently doing research in the Zurich University, but today I will talk about the research which we did when I was back at the University of Tartu, and the aim of the research was to see how X-Road is ready for the quantum age, what are the security risks in that regard, and what we need to do. So let's start with the basic info we all know about X-Road, is that it's open source software that provides unified and secure data exchange between organizations. And mainly when we here mean the secure, we of course think about the governance infrastructure, the trust infrastructure we're having, but all of that mainly relies on some cryptographic measures which are in place in the X-Road. So let me briefly introduce what is cryptography and why it's in general important for the quantum computing age. So when we talk about cryptography, there are three key types which our secure infrastructure rely on. First, there are hash functions. When we create hashes, we basically mean that there is one-way function which allow us to create some hashes which are pre-image attack resistant and collision resistant, meaning that knowing the hash, we cannot transfer back to the original plain text. Next, we rely on symmetric cryptography, where we use one secret key, which is both used for encryption and decryption. And in this context, we know that there is an assumption that it's very hard, it's computationally heavy, and takes a lot of time, like years, hundreds of years, to find those secret key in order to decrypt the ciphertext to the original data. So this is our main assumption for symmetric cryptography. And finally, we have asymmetric cryptography, which relies on the usage of two keys, the private key and the public key. And we have two main operations for signing and for encryption. And we assume that it is, again, computationally very hard and expensive to not knowing the private key to get anything valuable, like in any plain text, or get the actual private key not knowing it. So we rely on the hard problem of integer factorization and discrete logarithm problem. So these 5 key problems is what our cryptography, classical cryptography, relies on. But the problem with quantum computing is that we have 4 key algorithms called Shor's, Grover's, and BHT algorithm, which show that once quantum computing is in place, all of these previously mentioned hard problems are not as strong anymore. So we can do actual factorization and solving discrete logarithms, finding the keys and doing the backwards hashing in quite an efficient way. So specifically, when the quantum computing is available, when we talk about hashes, it would be possible to get the original plain text from the hash, or find 2 plain texts which would result in the same hash, which again we assume is not possible nowadays. Next, for the symmetric cryptography, it would be possible in the feasible way to find the original, to brute force the symmetric key. In terms of the asymmetric data itself, asymmetrically encrypted data itself, it will not be affected. But again, if key is available, then we would be able to decrypt the data. And additionally, symmetric cryptography is used for the specific key agreement mechanisms, and which also would be affected by the symmetric key search. And in terms of asymmetric cryptography, the appearance of quantum computing would mean that knowing the asymmetric public key, you would be able to again retrieve the original private key. For encrypted data, it would be possible to decrypt it backwards. And here is the main hot topic for now, is the harvest now, decrypt later attack, basically meaning that you can now already store the data which is encrypted and even though not having quantum computing in place, but as soon as it will be available and somebody can use it, then they will apply it to the previously harvested data and decrypt it. And finally, the quantum computing enables forge of digital signatures, meaning that not having the original keys, you would still be able to provide valid signature. So this is a brief intro of what quantum computing threats are in general out there, but what does it specifically mean for X-Road? So first, in order to identify what are specific risks for X-Road, we conducted the cryptographic inventory, which means that we wanted to define what are in general assets which are protecting now the business assets in the X-Road and how cryptography is helping in it. So in X-Road, there are 6 key business assets, including messages, logs, different configuration, and certificates. And knowing that these are the primary assets we want to protect, and accessing and going through the source code, documentation, and using the specialized cryptographic bill of materials toolkit, we identified that there are 27 different cryptographic assets which protects the data in transit at rest or helps to ensure security through support configurations. And when we apply those general quantum computing threats to this specific crypto assets, which includes all the different hashes created, encrypted data, signatures, protocols, keys, and so on, we identified that there are 32 main security risks, among which there are 4 of top key priority. So one of them is concerning the authenticity of the message, meaning that as soon, because of the quantum computing enabling forging of digital signatures, it would be possible to forge the message signature, so you wouldn't be able to recognize that the message was produced and signed not by a legitimate user of the X-Road, but actually by a malicious user. Another 2 big risks are related to the message logs. So as the messages are stored in the logs and then they later on transfer to the message log files for the long-term storage, because of, again, ability to forge the signatures, if the attacker gets an access to those logs or archive files, he would be able to also manipulate the data and forge cryptographically valid signatures, so that operators would basically, X-Road operators would not know that some logs has been manipulated and changed and think that it is valid data log. And finally, I would say the most critical, because of the time pressure, is the risk related to the storage of the long-term valuable data. So because of the harvest now, decrypt later attack, whatever currently an attacker is able to store, even if it's in encrypted form, as soon as he gets access to the quantum computing, he would be able to restore it. It may come after 5 years or after 10 years, but it's something that can be started to be implemented already now, even before quantum computing are available. In order to mitigate all the risks, we defined 11 key controls. But of course, primarily the strategy should be that we need to move from classical cryptography, which relies on all those complex problems, which I mentioned at the beginning, to the other assumptions. So of course, post-quantum cryptography, PQC, is the final solution, but there are also some ways, including these 4 corrective controls, which can help you to detect that something is happening, that there has been some attack already before you have post-quantum cryptography in place. So in the short term, first thing that both X-Road operators, users, and supporters should do is define what are their high-risk values and high-value assets, and start to transfer to the hybrid systems. So for the hybrid systems, currently there are options of hybrid signatures and hybrid PKI certificates. So this is something you can start doing already now. And to prevent and to be able to detect that there has been forged in the digital signatures, you already now can start adding the evidence to the signature creation, and it will help you later on to know that there has been a problem. In turn, of course, you need to migrate your data at rest for the post-quantum cryptography, which relies on the other systems to prevent the harvest now, decrypt later attack. You need to update to your PKI system, increase hash values and symmetric key size to prevent, again, fully prevent the PQ enabled threats. And there is already developed TLS version, which is post-quantum resistant. And of course, the ultimate goal long-term is to complete your PQC migration and move fully towards the NIST standardized algorithms. Currently, we have already standards for digital signature key encapsulation, but we don't have for encryption anything yet. And the final step would be basically abandon the classic cryptography for the high-value data so that you don't rely on the systems which can be broken with the quantum computing. Of course, there are a few challenges during this transition, including that because the quantum computing use different types of assumptions, different size of the key, it will impact the data sizes, which might affect the network latency, storage requirements. Also, there might be need to update your infrastructure, including procuring new HCM and TPMs, because again, the PQC relies on somewhat different hardware, which may increase the cost of the X-Road deployment. There might be some problems in the interoperability, because when you as an X-Road operator and multiple services who are using X-Road using different kinds of cryptography. So for example, somebody transitioned already to post-quantum crypto, somebody is still using old cryptography with the old PKI certificates, then of course it's hard to communicate and know for sure that all of this is working well. So again, there might be some transition of the incompatibility. And of course, what you can to prepare your expertise gap, because again, in order to be able to move to PQC, you need to have people who would be able on the X-Road operator side to support the PQC migration. So now we are at 2020, and the official plans, projections for the quantum computing being ready is the timeline between 2030 2035. That's been the official timeline for very long. Just recently in this April, we had an update that potentially the quantum computing would be more powerful than expected. So there might be already some feasible quantum computing in 2029, which gives us around 3 years until there will be something available. And basically we have 3 years to start updating and moving to PQC to prevent the leakage of our important assets already now. So let's start PQC migration today and hope it will not affect any of us. Thank you.